Welcome to the module titled, Microservices. The monolithic or traditional architecture services are a simple application deployed on a set of identical servers behind a load balancer. In contrast, a microservice application typically consists of a large number of services where each service has multiple runtime instances. But monolithic applications can also be difficult to scale when different modules have conflicting resource requirements. Hence, microservice architecture splits the application into smaller and interconnected services instead of a single application. Microservices optimize resources. A microservice helps multiple teams to work on independent services, enabling quick deployment and easy pivot when needed. For better understanding, let us take a look at an example of an e-commerce application. In this microservice architecture, each microservice is focused on single business capability. The search, rating and review and payment each have their instance, server, and communicate with each other. This communication is a stateless communication where each pair of request and response is independent. Hence, microservices can communicate effortlessly. Each microservice has its separate data store. This allows individual microservice to adopt a data model best suited for its needs. Microservice architecture is an architectural development style that allows building an application as a collection of small autonomous services developed for a business domain. In a microservices architecture, each service is highly maintainable and testable, enables rapid and frequent development and deployment, loosely coupled with other services, enables a team to work independently the majority of time on their services without being impacted by changes to other services and without affecting other services, independently deployable, enables a team to deploy their service without having to coordinate with other teams, capable of being developed by a small team, essential for high productivity by avoiding the high communication head of large teams, and scalable using containerization of each microservice. Services communicate using either synchronous protocols such as HTTP or REST or asynchronous protocols such as AMQP. Services can be developed and deployed independently of one another. Each service has its own database in order to be decoupled from other services. Data consistency between services is maintained using the saga pattern. When to use microservices. When developing the first version of an application, you often do not have the problems that this approach solves. Moreover, using an elaborate, distributed architecture will slow down development. This can be a major problem for startups whose biggest challenge is often how to rapidly evolve the business model and accompanying application. Using y-axis splits might make it much more difficult to iterate rapidly. Later on, however, when the challenge is how to scale and you need to use functional decomposition, the tangled dependencies might make it difficult to decompose your monolithic application into a set of services. How to decompose the application into services. Another challenge is deciding how to partition the system into microservices. This is very much an art, but there are a number of strategies that can help to decompose by business capability and define services corresponding to business capabilities. Decompose by domain-driven design subdomain. Decompose by verb or use case and define services that are responsible for particular actions. Example, a shipping service that's responsible for shipping complete orders, and decompose by nouns or resources by defining a service that is responsible for all operations on entities or resources of a given type. Example, an account service that is responsible for managing user accounts. Ideally, each service should have only a small set of responsibilities. The single responsibility principle or SRP defines a responsibility of a class as a reason to change, and states that a class should only have one reason to change. It makes sense to apply the SRP to service design as well. How to maintain data consistency. In order to ensure loose coupling, each service has its own database. Maintaining data consistency between services is a challenge, because two-phase commit or distributed transactions is not an option for many applications. An application must instead use the saga pattern. A service publishes an event when its data changes. Other services consume that event and update their data. There are several ways of reliably updating data and publishing events, including event sourcing and transaction log tailing. Now let us take a look at the challenges of microservices. The microservices rely and communicate with each other. In contrast to monolithic systems, microservices monitor services which are developed using different programming languages. Microservices have separate mechanism, resulting in a large amount of memory for an unstructured data. Microservice architecture brings plenty of operations overhead. How are microservices implemented? Client has API services packaged as microservice components, having their own database. Each microservice is independently deployed using CI or CD pipeline on AWS server and VM the servers. Jenkins is configured to set application properties and configuration. Jenkins then performs tasks such as building binary from the Git repository, creating a Docker image, transferring data to shared location, VM, and transfer image to OpenShift. You have reached the end of this module. Here are a few key points covered in this module. Microservice helps multiple teams to work on independent services, enabling quick deployment and easy pivot when needed. Microservices communicate using either synchronous protocols such as HTTP or REST or asynchronous protocols such as AMQP. Client has API services packaged as microservice components having their own database. Each microservice are independently deployed using CI or CD pipeline on AWS server and VM the servers.